So the first reaction would be our halogenation of the benzene ring. I'm going to use bromination as my example. And so that means that my two reagents are going to be bromine and the FeBr3 I have selected from my list of Friedel-Crafts catalysts, nice Lewis acid catalysts, in order to help me do this reaction. So we start off with a bromine. And there is an FeBr3. And the first step is that the FeBr3 activates the bromine by accepting a pair of electrons from one of the bromines. So now we have this species here. Now again, let's see what's happened in terms of our electrons. We have taken a lone pair of electrons from the bromine that it's donated to the FeBr, thus making a bond. Now that FeBr therefore got a bond for free, so it becomes negative, and that bromine has, instead of using one of its electrons to get one electron from the ion, is given both of its electrons for the bond, so it has a formal positive charge. Now at this point, of course, you've got this bromine that's rather electronegative, having electrons gone towards the ion, so it's going to say to its friend over here, the blue bromine, let me have some of your electrons. And that will now generate a slightly positive charge on that terminal bromine. And that is the electrophile in this case. Okay, you'd think, oh look, that's a bromine with a positive charge. No, this bromine is intimately linked with the FeBr3. It's the terminal bromine that has some of its electron density sucked away from it because of the creation of this coordination complex here, and so it becomes slightly positive. So now the mechanism, standard stuff that we saw in our generic one. The complex attached, the Lewis acid attached to the Br2 that has now activated this bromine here. So electron density moves from the double bond to the bromine. We get our bromine there at the end, says, well, you were taking too much of my electron density, have it all, because now I've got another friend over here. So we make the bond between the carbon and the bromine here. We break the bromine-bromine bond, and we get these two species there. So here again is how I am depicting our intermediate. I want that localized positive there so that we can see what's going on. Okay, and now at this point, we've got to abstract the H. What happens there is that this bromine here says, I tell you what, I would rather use my electrons on this H than I would that nasty old ion complex. So two electrons come from the bromine to ion bond. These were, if you think of it, these were the original electrons that were on that bromine, come there towards the hydrogen. The hydrogen then again says, okay, I've got a better friend over here with the bromine. You can take this ring electrons away. Two electrons move from the carbon-hydrogen bond to replenish the carbon-carbon double bond there. And we get our species. Now, of course, here is the bromobenzene that we wanted. We've also made HBr because we got the H there and the Br there. And of course, that's a strong acid, so we're just formally writing it as HBr. And then what are we left with? Well, we've got our bromobenzene, we got the HBr, we have the FeBr catalyst left back again to do another reaction. Okay, so how do we get the E+? We activate a bromine here as part of a bromine-bromine bond. The role of the catalyst is coordinate to the bromine, thus activating, as we previously said. And how do we get rid of the hydrogen? Well, that activated coordination complex comes back and grabs the hydrogen again. And it would be the same process for chlorination. So Cl2, use FeCl3, AlCl3, whatever grabs your fancy as far as the catalyst goes, but exactly the same activation of the chlorine and then abstraction of the proton.